So I'm Stacy McGaugh. I'm the token astronomer here. And I must say I am in awe of my colleagues who had prepared notes. I don't know what I'm going to say until I say it. In that spirit of preparedness, when Professor Rothman asked me for a title, I gave the first thing that came to the top of my head because I wasn't going to think about this yet. And so along the top there, I've sort of put a more perhaps musically connected idea, the cosmic harmonies amongst both the planets and the galaxies, because one of the things that resonates with our minds, whether we want to put this in terms of a theory or any of the issues that Professor Hoffa was just discussing, things that grab our minds are patterns in nature. And so this is something that Kepler came upon and cast an entirely new light on, and it's an ongoing process. So how do I advance this?
Put it inside.
Is this guy here? Okay. All right, so I was lucky enough to be in Prague shortly before the pandemic. So this is a statue of Tycho and Kepler in front of the Kepler Gymnasium there. These two had an interesting relationship, and I show this largely because nothing happens in a vacuum, even though Kepler clearly did burn the midnight oil and did do a lot of things just on his own gumption. And, you know, I would say, to sum it up crudely, Kepler was the brains and Tycho was the ego of this team. And he was responsible for doing a lot of essential things. He was, of course, brilliant in his own right and an extraordinarily skilled observer. And I only learned today that it's supposed to be pronounced Tycho. It's always Tycho to me. But so he built this elaborate observatory on the island of Uraniborg, basically, as near as I can tell, by virtue of moving his jaw and convincing the royalty to fund him. And he spared no expense of the royal purse in not just building an elaborate and scientifically useful large observatory, but also hiring an elaborate staff of artisans and people to build instruments that were useful, and eventually brought Kepler on as the sort of the mathematician to do the hard grinding. So in this depiction here, which you see a lot, he's pointing at that little slit in the wall. And so an important method of measuring positions on the sky was transit. Basically, you would watch when a star or a planet transited through a certain position. And by building this large observatory, he was able to measure those angles very precisely. Of course, the sky rises and sets every day. And the stars remain in a fixed pattern as they do so, and the planets move relative to the stars. And so in this fashion, he was able to obtain really accurate data, which were essential to Kepler's realization. So the three laws for which he's famous, the orbit of each planet is an ellipse with the sun at one focus, that really was the mind-blowing one. That, as Professor Hoffa just emphasized, for whatever reasons, people were obsessed with circular motion in the heavens. That was what was supposed to happen. And so to step outside of that and to say, well, maybe it's a different shape, was really, I think, as important as Copernicus's contributions to putting things putting the sun at the center of the solar system. Now, I want to emphasize how important it was to have good data. So what it was he was actually doing. And I've emphasized the quotes, which, you know, people used a lot of words back then. We're not very patient with that. But the essential thing is that if I thought I could ignore these 8 minutes of arc, then I would have just patched up my hypothesis, right? I could have made everything work. And this is what we're always doing in science. We don't want to go to that next step of completely adopting a new framework and abandoning the old one, unless there's something really compelling making us do so. And so this was, for him, the thing that said, no, I got to think outside the box. Why others didn't do that is a really good question. But it is a subtle effect. So you see the image over here is a circle. There's a blue line there. It's a perfect circle. A green line is the closest match. No, it's not a match at all. It's an ellipse with an eccentricity of 0.2. But it's a very good match to the blue line, right? Your eye can barely see the difference. And that's a big effect. Mars, which is, aside from Mercury, the most eccentric of the planets, and certainly the one he had the best data for, it's less than half of that in its eccentricity. So that meant that it was off by 8 arc minutes from what he could do. There's that diagram. What he could predict using any of the existing systems. And so this is one of his attempts to do so. And you see all these loop-de-loops. Every loop-de-loop corresponds to one of the retrograde motion periods, right? So around the edges are marked the constellations of the ecliptic, the zodiac. All the planets are moving in that same plane in the sky, and you mark their locations relative to the background pattern of stars. And so much like his triangle diagram that Professor Rothman showed us, he's basically traced out what the path needs to be. And this is in a geocentric system with the whole epicycles and also the equants. And it wasn't the epicycle that Copernicus objected to, it was the equants, wherein you had not just circular motion, but the center of the circle was offset. Right. And that, even learning that much kind of blew my mind, because when I was a young physics student, I was taught that epicycles were bad because they were a complication. And that's obviously true if you pile epicycle and epicycle and epicycle. And there did come a phase around here when, after over 1,000 years, Ptolemy was starting to get things wrong. And that's a pretty fabulously, successfully predictive theory. But by then, you were starting to have to make minor corrections and add little epicycles on top of the big epicycles, and then at some point you are chasing your tail, and how do you know when that's come to be? But people at the time were saying, oh, I've discovered a new epicycle in the orbit of whatever, and that's just silly to our modern way of thinking. But so Kepler made this calculation, and so the position at any planet, I just can't stand it. Start, finish, right? So this is not just the path that it takes, but as a function of time. So you can imagine drawing a line that intersects as a tangent on any date, one of those curves, and finding where the planet is predicted to be. And so this is what calculation Kepler had to make to test this. And he found a discrepancy of this 8 arc minutes. An arc minute is 1/60th of a degree. This is a tiny thing. And that was just under the precision that Ptolemy was able to do. Much like the geocentric system would have died immediately if Venus had a larger angular size, because then we could see its phases with our eyeballs. And we could see it went through the full range of phases, not just always being a crescent phase because it's between us and the sun. And it's close. The resolution of our eyes is not quite good enough. So maybe eagles have known this for a long time, and it took us a long time to figure it out. But there's also this notion of this obsession with circular motion, which, again, to our modern mind, looking back, the circle is just a special case of an ellipse, and all these conic sections are possible things, a parabola being the over-under point between something that's gravitationally bound and unbound, and a hyperbola being something that passes by, like, if something comes from interstellar space and swings through the solar system and by the sun, it'll get bent in its path in a hyperbolic path. So in some sense, this is a generalization, and the circle's just a special case, and that can be just as beautiful and compelling to our minds. But we've turned it entirely upside down. So it took him almost a decade to get to the third law, that the square of the sidereal periods scaled as a third power of the semi-major axes, the size of the ellipses. And I really do imagine him just, You know, he didn't have calculators and stuff like we did. He had to grind all this out by hand late at night. And how many times? Well, one power doesn't work. Let's try squaring it. Well, squaring it. Well, how about cubing? I mean, it's no wonder it took him a long time to get there. It's hard grinding work to do that. And so, you know, on the left-hand diagram is just that plot. If you plot the square of the period against the cube of the semi-major axis, you get a straight line all the planets fall on. And that, again, is something that's a harmony, right? That's something that compels you, that grabs your mind, that there is this pattern. They're not just all over the place. And I should say, too, he had to have the Copernican worldview in mind, even think about this period, because this is a sidereal period. That's not what's observed. What's observed is a synodic period. When does a planet return to the same part of the sky, from opposition to opposition or conjunction to conjunction or something like that? And that, of course, is a convolution not of the planet's period, but also of the Earth's, where we're viewing it from. So most planets have a synodic period about the period of a year, because it's dominated by where we're standing, not what it's doing. So you have to have a framework that lets you convert that to the true period of the thing going around independently of the Earth. So that's already a huge conceptual leap. On the right is the same plot, but cast in terms of a rotation curve, the velocity with which a planet is orbiting as a function of its distance from the sun. Of course, the orbits are nearly circular enough that this looks almost like a perfect line, though of course it's not this good a way of looking at it in the sense that the velocities do vary near perigee and apogee. But I do that to make an analogy to galaxies, which I study, and that's zooming out now by a factor of 100 million. So from the solar system, where we're talking about scales of astronomical units, out to the side of the galaxy, where we're talking about thousands of parsecs or light years. And the remarkable thing about galaxies is that they are not Keplerian. Those rotation curves do not fall off as the way that you saw for the solar system. They are flat. And of course, this was famously discovered by Vera Rubin, a number of other people, but Vera really advocated and pushed for this and measuring it over and over. She told me the story of measuring this for Andromeda, which is the nearest bright galaxy to us, and having Alan Sandage, a very eminent cosmologist at the time, dismiss it and say, oh, that's just the effects of looking at a bright galaxy. And she's like, what? Because it made no sense. That comment made no sense whatsoever. But it was just, you know, that's not right. That is our reaction to hearing something not right. So here you see many examples where she measured out, went and out and over, and this is just one of a series of papers she wrote at the time showing it in 100 cases it was always flat. So there's a picture of Vera with her husband Bob with the Magellan telescope in the background in Chile. Now, I think it was still under construction at the time. In fact, it had to have been, because I haven't been back there since. And so I'm sure people will speak in the future about her the same way we do about Kepler now, because this is really changes our worldview in profound ways. And so this is the quantitative look at that. You can calculate from using all the mechanics of Newton and everything that was learned post-Kepler, but it still comes down to that same shape, that it depends on the mass of the object and how far away you get. And you can predict what that looks like, and that's that black line falling down. That's what we call the expected Keplerian behavior. If what you saw was what you'd get, that's what the rotation curve of this galaxy should be. That upper line that goes through all the data, that's what we see, right? So galaxies do not behave in a Keplerian fashion. And so the interpretation of this is to add two Keplerian components, that the galaxy is embedded in a larger halo of invisible mass that we call dark matter. And so that blue line, that is the total, is the combination of the declining luminous matter and the increasing contribution of the dark matter, which has both a bigger mass and a bigger scale radius. And, you know, you have to arrange it so that they contribute enough to keep things flat, just so. Now, that was well known when I entered the field, as was this thing called the Tolley-Fisher relation. But it took a while to put things together, and in a nutshell, the amplitude of the speed, how fast a galaxy spins, depends on its mass, the mass of the stuff you can see. And that's what this Tolley-Fisher relation tells you. So the flat rotation speed is really big for a really big galaxy, and small for a small galaxy. And so you can plot that together. So there's the mass on the y-axis and the rotation speed on the x-axis. And every point there is a galaxy. And I was interested in these dwarf galaxies that are more gas than stars. So the lighter blue points are things that are more gas than are stars. And the darker blue are more stars. And if you count all those components, you add everything up, then you get just this one power law. But what you don't understand is why there is no residual with size, right? It's the mass over the radius should give you the velocity. And so I had a prediction for these low surface brightness things I was working on that had larger radii for the same mass, and they should have deviated from this Tolley-Fisher relation, as it was known at the time. And that's what that red dotted line there is in the residuals. I was wrong, right? The data do not do that. That was my prediction, and it's not really my prediction, it's Newton's and Kepler's, right? And so the only recourse in this picture is to basically play a fine-tuning game to balance what the distribution of the stuff you see is doing against the distribution of the stuff that you can't see is doing. And of course, you're free to do that. This is a curve fitting exercise because you can't see that one component. So you're free to do that, and it always works. But there's something more to it. And so I've plotted here all the rotation curves I could put my hands to, color-coded by the effective surface brightness. That just is a measure of how concentrated the stars are. High surface brightness, the stars are relatively close together. Low surface brightness, they're spread apart. Okay? And you can see there's almost a perfect rainbow here. Right? The low surface brightness galaxies have slowly rising rotation curves, tend to have lower amplitudes, and as you get to higher and higher surface brightness galaxies, they go up more and more quickly. This is an example of the harmonies I'm talking about. There's a clear pattern here that you can see with your eyes. You don't need any framework, mathematical or otherwise, to see that there's something systematic going on. That tells us something about how the universe works. We can argue forever about what that means, but it's telling us something. And so it's a pattern that's different than the pattern that Kepler discovered. This is what I call the radial acceleration relation, and so now we're plotting the centripetal acceleration that's observed, so sort of the force that's required to keep a star in its orbit, plotted against what's predicted by the whole mechanics of Newtonian dynamics. And if there were no dark matter or whatever funny business is going on, then everything would be on the straight line. That's the prediction of Newton and Kepler, really. But you can see there's a deviation from that. The data, as you go to low acceleration, bend upwards. And that difference is entirely what we call dark matter. But it's connected to the distribution of luminous matter. We can calculate it just based on what we see. And so this is a pattern. This is some kind of harmony, and there's a new scale here that's unknown to physics before. It's basically an acceleration scale that's somehow special to galaxies. That's just in the data. And so we can zoom out. This is the same plot now, but covering a much larger range so that I can encompass the solar system, where Kepler, you can see the planets in this plot all follow that straight line. That straight line is what's predicted by Newtonian gravity, going all the way up to the top. You are here, where you feel about 10 meters per second, sitting in this room. Right, and then as you go out in the solar system, the forces that the planets feel get less and less as they get further and further to the sun, because of the famous inverse square law. But when you get to the scale of this new number, you bend away from that one-to-one relation, and that's where galaxies live. And they follow this new relation. So there is an extension of this harmony, and they're connected in some way. And it is our job as theorists to try to understand what that is. Thank you.
Thanks, that was awesome. Do you have any, I mean, just in your personal experience, so you see Kepler kind of grappling with the problem of what to do with my Platonic solid model, because it doesn't seem to be fitting right. I mean, do you have like a articulatable sense of what you kind of go through when you're looking at gaps between predictions and observations?
Pain. I mean, the sort of story of how I personally got onto this involves that failed prediction. So I thought I was on to a way of understanding low surface brightness galaxies, which I had been working on at that time, and that was my personal obsession. And up until that point, it had been largely ignored in the field. And in fact, there was a thing called Freeman's Law at the time that asserted they didn't even exist. So, you know, one thing was demonstrating they exist, but the other thing is measuring their properties and trying to learn from that. And that made a great test of galaxy formation theories at the time, because they had mostly been tuned to explain Freeman's Law, things that we exist. Here, okay, here's this new kind of thing that you weren't really thinking about. So it pushed the theory into a regime that it wasn't designed to cope with. They all failed, including mine. So what I had learned, and of course it's an iterative process, so what I had learned up until that point about low surface brightness galaxies told me that they were just diffuse systems. Everything about their properties were because the stars were more spread out. They made them slower, they evolved more slowly. And that led me to two predictions that were genuine a priori predictions that could be tested. One, they will have that property if they form later, and then they'll be lower density just because the collapse time takes longer, and that's how the dynamics works. In which case they should be distributed more diffusely than regular galaxies. So if you imagine, if you've seen the pictures of the large-scale structure of the universe, these very filamentary structures, they should follow that, but not as tightly. And I didn't know how to measure that, but by good chance, an office mate of mine in Cambridge, where I was a postdoc at the time, did. And we got to talking about this, and I was like, well, this is the obvious consequence, but I don't know how to measure it. He's like, oh, I know how to measure that. And so we did it, and it was bang on. And that was not a quantitative prediction. It was sort of, you know, it had to shift in that way, and that's what we saw. And so I was very full of myself at that point. We got this. The second prediction was that there's a lower density for the same mass. You're spread over a larger radius. That means the velocity has to be lower. And so they should shift off of Tully-Fisher. Well, no. So I really spent a lot of time saying, well, how could this be? And I made up all sorts of, you know, exactly as you described. You just go in circles trying to accommodate that. And I found lots of ways to do it, but none of them that I found to be satisfactory, because it always seemed that I was invoking a tautology. Oh, this does it. Oh, well, but wait, I assumed that when I built this particular model, and that has the necessary consequence. And frankly, the history of the field since then is people reproducing those tautologies without recognizing that's what they're doing. Because it's the desired answer. It's within the framework that we currently have. You need to do something like that without, if you don't want to abandon the framework, which nobody wants to do.
I'd like to ask kind of a related question, which is like sort of this, you know, open questions about why do we see these deviations. And of course, some people attribute it to dark matter, others to modified gravity. I was wondering, what do you see, what would be the thing that could resolve that and convince everyone one way or the other?
Well, that's a great question that I've been asking myself for over 20 years now. And the first answer I came up with, because for the home audience, there are really two rather different ways that you get into the dark matter problem. One is the dynamics of galaxies and other extragalactic systems that I talked about. The other is cosmology writ large. Einstein's general relativity provides a really good description of how the universe evolves and expands over time. And that works now if and only if you have dark matter and also dark energy, right? And so if you assume that, if you start out with that blinder on that it has to be that, then you're inexorably driven to conclude that those things are true. So from that perspective, this is just all details to be worked out. From my perspective, this is a fundamental cosmic harmony that should be driving. There's clearly one force law at work in galaxies, just as Kepler's law led Newton to realize there was one force law working in the solar system. And the thing that troubles me is that, if we're going to say we explain that with dark matter, it's like saying, well, we can explain the solar system with an inverse cube law. There just happens to be dark matter distributed just so that it always looks like an inverse square law. Right, and that's insane to our way of thinking. But that's exactly what we are doing with dark matter in galaxies right now. I would make this argument to cosmologists, and they cared not one whit about, oh, galaxies are small. I don't know, 100,000 light years strikes me as kind of big. But to the mind of a cosmologist, that's small. And small scales are nonlinear, and so anything goes, basically. And they're obsessed with being able to solve linear perturbation theories on large scales where everything is just YAR and clean and very simple. And of course, it's the other way around. Once you adopt a modified gravity solution, it's galaxies that are simple because it's just centripetal motion in the force law, and you don't even have a theory that addresses cosmology, right? So it's very hard to switch hats and think about it fairly both ways. So my first thought was how to explain that was to make a prediction for the microwave background. That came true, and nobody cared. Or else maybe they did care, because I've only recently become aware that there's this sort of background chatter as to how that didn't even happen. They didn't bother to read the papers or the numbers. They just said, oh, well, that was wrong. And so I still wonder, how do we get out of this? And it's tough, because you appeal to arguments. You appeal to the philosophy of science, to, the rule of parsimony, and none of, both sides will claim this. So just to give one more definitive answer, right now the limits on neutrino mass from atmospheric oscillations, you have to have at least 0.06 eV in the sum of the three neutrino masses, just to have those space for the levels in the neutrino hierarchy. On the other hand, if you have too much mass in a hot dark matter component, then it really messes up our standard picture of the structure formation. That is the linear theory that cosmologists are so happy about. And so the limit on that side is an upper limit of 0.12 EV. So there's only that narrow factor of 2 window in which the neutrino mass has to reside, the sum of the neutrino masses. Well, experimentally, we're still up around 1 electron volt. So if some experiment like Katrine actually measured it was 1 or half an EV or clearly above that 0.12, then I think that would be a definitive sign. But if it's not that, then we're still just left arguing about which is better, right?
In the previous talk, Professor Hoffe mentioned that in these kind of disputes between a theory that's more accepted and more maybe has more of a history and a new theory that's come along, oftentimes both sides claim the same value and virtue of their theories. Do you see anything like that with dark matter or modified gravity?
Well, so in this case, I do put a lot of weight on a priori prediction. And so I just bragged about how I got one prediction right, but also admitted how I got one wrong. Everything I just showed you, though I didn't mention it, was predicted by a modified gravity theory that Milgram wrote down in 1983. And at the time, people didn't think low surface brightness galaxies existed. But he said explicitly that they would be on the same Tully-Fish relation. He said explicitly they would have the kind of rotation curve shapes that we do. And that does appeal to my mind. He could write it down, nerding out all on his own. He wrote down this set of predictions, and they came true. That has to mean something. Now, I'm open to it meaning something more than that. His theory is not complete in the sense that we're used to meaning that. But I would also think that any sensible approach would start from there and build on that. And that's not what we're doing. We're saying, no, we are already committed to dark matter, and so we're going to keep adding our epicycles there until it works out. And we can do that because you have it really is an epicyclic theory. You have an infinite number of free parameters to play with because you can't see this stuff. I find that very unsatisfactory. Okay, well, I think my dear colleague from physics, Harsh Mathur, is up next. I'm really excited to hear what he has to say about this. Thank you.